Okay, so good morning, everybody. My name is Rosario Fazio. I'm at the International Center for Theoretical Physics and Trieste Institute for Quantum Technologies, and welcome everybody here in the room and all those people that are connected online. So it's a great pleasure to have this panel discussion here with two distinguished speakers, Professor Tommaso Calarco, who is present here in Trieste, and Professor Latorre, connected remotely. We are going to discuss about quantum technologies and their impact in our present society and in the future. It will be a discussion, so it will be pretty informal, and we expect questions from the participants. Those who would like to ask questions here, they should move somewhere in the room, and they will be allowed to ask questions. Those people that are connected online, I think I will receive questions here, and I will forward to our speakers. So let me first introduce Professor Latorre, and then Giuseppe Santoro, who is coordinating with me this section, will also introduce Professor Calarco. So Professor Latorre is currently director at the Center for Quantum Technologies in Singapore. He has been giving many seminal contributions in various areas of quantum information. He has been working at MIT, then for many years he's been professor in Barcelona, and recently moved to Singapore to the NUS to lead the Center for the CQT, Center for Quantum Technologies. So he has been working on several directions connecting quantum information to high energy, complex quantum systems, simulations, and today will share with us his views on the impact of quantum technologies for the future. So I just leave the floor to Giuseppe to introduce Professor Calarco.
Yes, good morning, everybody. I'm Giuseppe Santoro. I'm professor at CISA, in particular in condensed matter theory. I obviously collaborate with the CISA faculty and with Professor Fazio on the Trieste Institute for the Theory of Quantum Technologies, so trying to foster activities in the theory of behind quantum technologies. So we'll immediately jump to presenting Professor Calarco, who is currently the director of the Institute for Quantum Control in Jülich. Optimal quantum control is one of the fields that he has pioneered, in particular applications to many-body quantum systems and quantum computation. So Tommaso received his PhD from Ferrara, then he moved to the group by Peter Zoller in Innsbruck, and then he moved to the Bose-Einstein Condensation Center in Trento, and from there he started his brilliant career in Germany, first in Ulm, and more recently in Jülich, and he has been really a leading figure in the European community policy for quantum technologies. He's author of the Quantum Manifesto in 2016, and he has initiated the European Commission quantum flagship. Currently is the chairman of the flagship governing body, the Quantum Community Network. So certainly he's the right speaker to tell us what's going on in Europe about quantum technologies. With that, I think I leave the word to Professor Fazio, who will start with
Okay,
questions.
so I think it would be interesting to start with a little bit of history, and I will ask both speakers to tell us just a general introduction to quantum information processing, the main ideas, physical ideas behind it, and if they can also tell us a little bit of history since they contributed to it. I don't know. Probably, who wants to start first? Either Jose Ignacio. Jose Ignacio, do you hear us?
Hear me?
Yeah.
Okay, that's good. No, I'm happy that, whatever, Tommaso may start. I'm very happy to listen first.
Well, I can start with a personal note, because this is a question for me, which this is the right place to be asked. Because when I was a student in a different university, it was a long time ago, my goodness, it was like almost 30 years ago, I was in Padua, and for a series of situations, let's say, I came here to Trieste, and actually my idea there was to work on some chaos theory, some classical physics. And at the time, there was no such thing as quantum information. There was nothing like quantum technologies. It was something utterly useless called foundations of quantum mechanics. And I really didn't think about moving into that field. But I came to Trieste, and in a series of seminars, I met some of the protagonists of the field of quantum at the time, including the late Giancarlo Ghirardi, who, by the way, and this is something which even many colleagues do not know, he was among the first to prove the famous no-cloning theorem, which at the time, and this is why I think this is a nice Trieste story here. At the time, it was just a purely almost philosophical concept, the fact that you cannot clone a bit of quantum information, but then it immediately became, almost immediately, over the space of a few years, it became really the basis, one could say the foundation, but in a different way, the basis for this amazing technological development. And why is that? Because the fact that quantum information cannot be cloned, we know that there is the Heisenberg uncertainty principle, we know that there is measurement theory in quantum mechanics such that if you observe an object, then you change its state. And this seemed something purely philosophical, as I said, for many years, until a few people realized that the implication of this, since you cannot copy some quantum information, it also means that if you use quantum information, in this case to transmit some message, then someone who will try to copy it will not be able to do that. So an eavesdropper will not be able to intercept that information. And so immediately there is a transition between this very foundational, fundamental, utterly useless thing, which was actually what fascinated me in Trieste at that time, and still does. Well, it comes from a purely curiosity-driven field to a field in which nowadays you can buy devices which realize that, which send single photons and encode messages which cannot be cracked. And as a matter of fact, and we will come back to that probably later on, nowadays the Commission is planning, the European Commission is planning a multi-billion euro initiative, the European Quantum Communication Infrastructure, and there is going to be a little demonstration exactly of that today, involving our Prime Minister, as a matter of fact, again here in Trieste, well, using those very ideas which historically came from philosophy and now turning them into devices and ultimately making available the benefits of this for the whole society. Now, there are other stories like this in other fields. Maybe I don't want to speak too much in this first introduction.
We have time. So.
We have time. But, well, let's say I would leave a little bit, maybe Jose Ignacio to speak a bit, because then there are other, as exciting developments concerning entanglement and quantum computation and many things of the sort, which we can come back. But I really wanted to start with this really Trieste thing, because not only 30 years ago, but also today, Trieste is very much at the center of these developments. So for me, it is not only emotional, but especially, I would say, even politically relevant to have this session here today.
So, Jose Ignacio, do you want to tell us also your views?
Yeah, Rosario, hi. Well, let me tell a little bit also how it was for me at the beginning of quantum information. So it was in the middle of the 90s, and I was working in high energy physics, both in really theoretical aspects in renormalization group or in phenomenology. But we decided to set up a small group of people to read papers on these new things that nobody knew. There was no name for that. And indeed, our first journal club was on quantum compression, Schumacher's algorithms. Then we learned teleportation, and we remember distinctly, and only then we went to Shor's algorithm. And at some point we said, well, should we take this seriously? And the idea was to direct a PhD thesis. So when we decided to jump on this new field, we started to study optimal measurements. I remember distinctly that we didn't know the name of the field because we had to organize something, and we were just checking how do we call this new subject. But the relevant thing is that for some of us, it was so clear that there was a gigantic field emerging. So in a way, let me put it in this way, humans had reached control of individual atoms and individual photons, and that is just a dramatic change. It's a technological change that introduces the possibility of going much deeper in the theoretical aspects and in the practicalities of what can be done with these developments. So immediately it was clear to me that there would be a relation with condensed matter, and Sarah is an example in your group of big developments in the relation between quantum information and condensed matter. And it was also clear to me that communication would be a big thing, but that quantum computation was a possibility that was very, very real. I must say that for many, many years, most of my colleagues thought that this was a little bit crazy. They put it in the category of, unachievable goals. Whereas other people, in particular in North America, they considered that this was a solid reality. So in a way, for me, the history of quantum information has been a history of seeing how people that didn't believe that humans can have such a control of nature would little by little accept that the progress was being done, and it was extremely solid. So nowadays is really, I think, a fantastic situation where we have no doubt that we have a new revolution of quantum technologies going on, and that these will have a real impact in economy, in industry, and also in the future science. Let's always remember that present science is what we need to create instruments for the next generation of science. So I think that it's a success story, the one of quantum information, although it was not a trivial one.
So, but can you summarize in few words what is quantum information? Just what are the basic principles?
Let me tell
Well,
you.
I can.
Good.
Sorry?
No, go ahead. You go ahead, and then I have a little story to tell.
Yeah. Well, I have a way to understand things that may be a little bit awkward, but so I try to see science as a whole, and I cannot go back to the Greeks and the Jonic schools, but let me start with Newton. In the 17th century, actually, with the philosophers that provide the grounds for Newton, la méthode de Descartes. But then you have a century which is mechanics is the elements of the century. 19th century can be seen as the development of chemistry. But then 20th century, the first half of the 20th century is definitely physics through all the relativity and quantum mechanics is a big, big jump and a new instrument. Second half of the 20th century, it's often referred to biology as a big field that developed. But there is where I see a difference. I think that that is also the beginning of information theory. That's a big step, which Shannon and all the followers is done in the second half of the 20th century. So let me simply say that this quantum information that we are witnessing in the beginning of the 21st century is just a natural blending of all our understanding of nature at the level of quantum mechanics with the profound ideas of information theory. And this is what makes quantum information such a powerful field. This is simply saying that we want to communicate, we want to store, communicate, and manipulate information, but the means to do that are not the laws of classical physics, but the laws of quantum mechanics. We do have concepts such as superposition that are dramatically different from the classical world. They do not exist to the quantum world. And the processing of this quantum information is also different. We have unitary, reversible operations, which are not which is not the scheme that we use typically in the classical world. So quantum information is hinting at the same idea, which is how we deal with information, but with new tools and much more powerful tools. So I think this is why this is not to be considered as a fashion or as a wave of interest. It's a profound field. It's a deep idea. Maybe, Tommaso, you can.
Yes, I have another little story to tell, because somehow, you know, Saro here asked, can you tell us what it is? You know, what are those qubits? And well, I already gave an example of that when I said that if I'm sending single photons and then they cannot be cloned, then it also means they cannot be intercepted. But this is just one example. So let me tell you another story. And actually, it's nice. It connects to something which Jose Ignacio said before, because he said, you know, people, even the founding fathers of quantum mechanics, they did not really believe that you could really use these things. In fact, for many years, this was thought to be purely a domain of a philosophy. Does reality exist? Does a quantum mechanical object possess properties before it is measured? It seems really purely philosophical. But then experiments came. As a matter of fact, among the founding fathers of quantum mechanics, I think it was Schrödinger, who said, well, it is ridiculous to imagine, to make experiments with single atoms. This would entail inevitably ridiculous consequences. It would be much more reasonable to imagine that you can raise a pterodactyl in a zoo. Now, nobody knows why he chose a pterodactyl, you know, but this is what he chose. And this was just to say, you know, it will never come. In fact, such experiments were called, since all these people were Germans, they are called, even in, I remember in Italian lectures of quantum mechanics, we would speak about Gedankenexperiment, like the professor would say, e adesso vi spiego questo famoso Gedankenexperiment. So it is one of the few words in German which are used in Italian, in the field, I mean worldwide, and it means something which only happens in your thought. As a matter of fact, we all sitting here learned in school that you cannot see a single atom. Actually, I found out that my children still learn in school that you cannot see a single atom. And then, here is the story. When I was in my second week as a postdoc in Innsbruck, as Giuseppe reminded us, well, there I take my bike outside of the cellar and I wanted to go back home. And in comes a black limousine. And out of the black limousine comes the Dalai Lama. And His Holiness had come to Innsbruck, well, on one end to visit Anton Zeilinger and speak about teleportation, and we'll come back to that later. But what is relevant for the present question is he came to Innsbruck, to the lab of Rainer Blatt, to do what Schrödinger thought will never happen. To do what our children are taught in school that you are not going to be able. In fact, he went to the lab. There was a little vacuum chamber. It's like a can of glass, like this. And then there is a microscope. And inside the vacuum chamber, there is a single atom which is trapped. And between the atom and your eye, there are only lenses. It's a microscope. No fancy thing like electron microscopes or strange stuff. Just lenses. You wait 5 minutes in the darkness, and then you see this thing. You can see this little tiny atom, which is lonely in the darkness, little greenish, glowing. And this is something which, in those years, was just starting the ability to manipulate individual quantum objects, something which had previously been thought to be impossible, and now happens routinely in labs around the world, and this is the main foundation. So if we think the simplest thing about quantum information is I manipulate individual quantum objects, an atom, an electron, a photon. Now, José Ignacio hinted at some of the properties that these things have, like superposition, entanglement. What is superposition? Well, superposition is something which we don't have classically. Like I have this bottle of water here on the table, and the bottle of water can be, I can put it here. Of course, I have to be careful with the microphone because there is COVID and all sorts of things. So I put it there, or I put it here. It cannot stay in both places. You now see two bottles because there are actually two of them, but you cannot have one bottle in both places at the same time. Well, this is what happens with a classical object. If the bottle was an individual atom, you could have it both here and there. If we now use, there are two tables here, for you, this is the right table and this one is the left table. And we can say, okay, here is a bit. I use this system, it's a bit cumbersome to do that, but I could use it to encode information. So let's hide the second button here behind. And now I can have, if the bottle is here, my bit is in state 0. Here, it's in state 1. A classical object can only do this once at a time. However, a quantum object can do both at the same time. A quantum bit can be in 0 and 1 at the same time. Maybe with 50% probability 0, 50% 1. Maybe 30, 70, maybe whatever you like. So it means that a single quantum bit, the unit of quantum information, can explore different possibilities at the same time. Now, if I have only one of these, not much happens. Again, it's a toy for the amusement of physicists. If I have many of them, Google had 53 a few months ago. I will come back to that in a moment. If you have many of them, what does it mean? Let's imagine that we have to solve some problem. How do we do that with a computer? We calculate. There are bits, and we add, subtract. We combine them. Let's take an example. That my problem is finding the way out of a labyrinth. And now, how do I do it normally? I will try, and now there is a bifurcation. Do I go left? Do I go right? 0, 1. And then I try to go right. And then I follow a path, and then I hit a wall and say, this doesn't work. Let me go back, let me try another one. And then this time I went right, and no, let me go left. And then I do another path. Now, this is what I can do with classical objects, when I can put my bottle left or right, my qubit in 0 or 1. But if now I have quantum bits and many of them, I can go both left and right at the same time, just in one go. In one go of my quantum computer, I will be able to explore all the paths in my computational space, all the possible solutions to my problem. So I run it once, and I get the solution. It's like, instead of running myself through the maze, I just get a very big bucket of water, and I pour it there. And then I find out where it comes out. And there is my solution. And in fact, this is a nice metaphor because quantum objects, and this is why they behave like that, they do behave a little bit like water. They behave like waves, you know? This is also one of the things that, you know, we hear possibly even in James Bond movies nowadays, you know, the wave-particle duality. Quantum objects not only are particles, but also move like waves. And these are those possibilities which, when the Dalai Lama came to see the atom, it was just as a fundamental curiosity. But now, Google put 53 of those qubits in a superconducting circuit, and they solved last year a problem which it took 2.5 minutes for them to solve, and for the most powerful supercomputer on Earth, it would take more than 10,000 years, and the quantum computer by Google runs by 26 kilowatt, and the supercomputer takes 14 megawatts. You multiply by the number of years, that is also something which has some effect on energy consumption for computing. Nowadays, you know, percents of the world's energy consumption are used for computing. So this is, again, another connection between the elementary aspect and how those individual quantum systems are units of quantum information and how you can make something useful for society. So I hope that clarifies a little bit more what that is.
Perfect. Yeah. Thank you very much, both. If I may, just since we are talking about the past, then we'll approach present and the future, I really would like to ask to both if they think there was a kind of turning point in which there was a real boost and people realized that quantum information was going to be very useful, or it was something progressive. Jose, Ignacio, do you want to say something? And then Tommaso.
Yeah, certainly. Well, I think it was more of an incremental conviction, as far as I can tell, although it was punctuated by many individual successes. You know. I think that communication was showing very, very soon that there was a future for it. We may remember all that one of our colleagues founded ID Quantique, the first company that was promising quantum cryptography and quantum key distribution. Let me also mention that the appearance of transmons, that was a big thing. Okay, when it was possible to create a superconducting qubit, I remember that as a really step forward. And other pieces of quantum information, like quantum sensing, is like a silent revolution. No, it's little by little we have a much better control of nature, and it is increasingly clear that sensors can jump in quality and in performance. So, to my understanding, this is like a little incremental progression. But at some point, what happened particularly in the European Union, and Tommaso can bring a lot of information on that, when the flagship was conceived, I think this was really a turning point for many researchers in Europe and also for the rest of the world, for people in Asia and North America. It was like for the first time, Europe as a whole embraced quantum information. It organized in the famous pillars and horizontals, and that was like bringing structure to the research of the next decades. I think this was crucial in a way. So although the physics, as I said, had really relevant milestones, and the progress was clearly ahead, incremental and very solid, I think that it was at some point the political conviction of the European Union that really put everything in place. I think Tommaso can say much more than me on this issue.
Maybe I will tell later the story, how the switch came with the European Commission. It was I will tell that story later, but I have another story now, which is about those milestones. Well, of course, what Jose Ignacio said is very correct. However, there have been a few, spikes, like in 1984, when the Bennett-Brassard BB84 protocol for quantum cryptography was invented. in which it was shown that this no cloning theorem, which Giancarlo Ghirardi here in Trieste co-discovered, as we said, could be used to make information uncrackable. This was certainly the start of a development to make that real. And another one was in 1994-5, in which Peter Shor, a mathematician from MIT, invented the Shor's algorithm, which also Jose Ignacio mentioned before, which is an algorithm with which a quantum computer can factor numbers much more quickly than a classical computer. And the little story I have to tell, because this is, as Jose Ignacio correctly pointed out, always connected to politics, is when I think in the late 90s, there was a discussion in Washington, D.C., in which Jose Ignacio's predecessor, Arthur Eckert, was present, as well as my colleague from Jülich, David DiVincenzo. And this was a discussion with some high-level representatives of the Pentagon to tell them that this stuff could be very relevant for secure communications, as well as factoring numbers, which the Shor's algorithm can do, is relevant for strategic developments because it can allow to crack classical codes. And so those two scientists, by the way, two theorists, and this is again relevant for Trieste, I will tell that in a moment. So these theorists, they said, there are these very nice developments, this is very cool stuff, you should look into that. And the generals were more or less, dozing out. And then the meeting was over with really no conclusion because, it's kind of some scientific thing. And then Arthur, just when he stood up and before going out of the room, said, and by the way, the Russians might get it first. And some people woke up, they opened their eyes, and they decided to fund the first program in quantum information in the US. So that's the unfortunate part, because also my story with the Commission, is partly connected, not to the Russians in this case, of course, but to something like this. That's the unfortunate part, because there is a feeling, we have to be strong, we have to beat the others, like, the space race. Whereas, as a scientist, I don't see that this is the right attitude. The right attitude, as Hartmut Neven, the boss of Google Quantum Lab, says, it's more a race, mankind against nature. It's about controlling this phenomena. It's really something where we should unite forces. And again, such a forum, a science forum like today, is the right place to discuss this. But of course, we have to understand that there are also strategic implications, so sometimes this helps decision-making. But what I also wanted to, the point I want to make, just to finish this historic part, is, look, all these people I mentioned, Shor, Eckert, DiVincenzo, but also Bennett and Brassard, who were mentioned before, those were all theorists. Why is this relevant? Well, I'm telling this to Professor Fazio, who is an eminent representative of the International Center for Theoretical Physics. I'm a theoretical physicist, and by all respect to our experimental friends, this is really something where the role of theory, historically and also still nowadays, is very strong. So once again, we are in a place which really has a very strong track record, competence, and possibilities to really, push forward this revolution.
Sorry, I was just reading because there are already a couple of questions for the... but we go on and then we will go.
No, that's fine. I'm done.
Okay.
Yeah,
Saro, may I add something on this?
Sure, go ahead.
Because I wanted to add to Tommaso that also the control knot by Sirac and Zoller was something very relevant, again, theory people providing the idea how this could be done in practice. But I wanted to add that I think that the time is such that theory and experiments should merge much more than in the past. To give you an example, one of the things which we are doing now at CQT is that we had a division in theory, experiments, and exploratory, and now we will have a different structure where theory and experiments are together in the in the domains that should be together. So actually, I think that the conversation between theory and experiment should be extremely close in this new era. I think that theory people should know in detail what experiments are and vice versa. I think this is something that is a necessity for the development of our field. It's simply going in that direction, my comment.
Okay, maybe I would return a bit to things that have been mentioned already, but it's interesting to discuss. I mean, what is the current impact of quantum technologies? What are the, apart from quantum cryptography, and what are the expectations for the future, for the near future? What is the time span that you expect for things to happen?
Yes. Well, you mentioned quantum cryptography, of course. The current impact is the possibility to secure communications with commercial systems across distances up to a few hundred kilometers. And this is what I said before. Now the qualification that I'm bringing here is that it doesn't go much longer than a few hundred kilometers. And so the next aspect to bring it to continental scale is to develop what we call the quantum repeaters. So why not more than a few hundred kilometers? Because those photons which I'm sending, as I said, they cannot be copied, which is good because it means I cannot intercept them. It's also bad because it means I cannot amplify them. So normally on standard transmission lines, you have some repeaters which read the signal, which maybe has some noise after several kilometers, and then it amplifies it, it regenerates it. You cannot do that with a quantum system because otherwise it would destroy the state. So you need, instead of measuring and amplifying, you need a little quantum computer, really a quantum processor. So this is the connection to future nodes of a quantum internet to be able to establish such entanglement in that case on a longer distance. Actually, we didn't touch yet upon entanglement, so maybe we do that later. We will speak about teleportation perhaps and these things. But this is sort of the next stage, creating little nodes of an elementary quantum internet across Europe and across the world. Actually, we also have, I was at the White House last year a couple times to negotiate a cooperation program with them. And now the plan is really to try and create a transatlantic link, which would be based on quantum repeaters and possibly on satellites, and also we'll come back to that later. I have another story to tell about teleportation. But in any case, the future impact is the expectation, if we manage to create those little quantum computing nodes in the quantum internet, to have Europe-wide secure communication at continental scale. Now, what is the impact of quantum computing? Which is the fact, using many qubits, as I said before, to find the solution of a problem. Well, at the moment, as I mentioned, there has been last year this amazing result from Google, but it is more like the Brother Wright's flight. So it's fantastic milestone. It's an enormous engineering achievement. It is completely useless. Because, to fly for 100 meters, at a level of maybe half a meter, a couple of meters above Earth, well, I mean, I can do it myself with my bike, if I have to transport something. But I don't think that we have to argue today what was the value of that. It was something which per se was useless, and it opened the way to something which was really a complete revolution. So the problem which Google solved, which the supercomputer takes 10,000 years, is a completely abstruse, artificial, academic problem, which was conceived only to show that it is something which the quantum computer can solve and the classical computer can't. It is something which even among colleagues, when it was announced, in every faculty virtually on Earth, there were seminars trying to explain to each other what is this problem, because this was so completely artificial. It is, sampling in a random distribution of unitary transformations. Okay, does it tell you anything? Well, even if you are a physicist, it might not tell you very much. Once again, It's something which was invented by some theorists. So we do need those theorists to drive the development. So the impact now is, which actually, if you ask me like 3 years ago, I would have told you, and this was the official line of our community, it was even written in the Quantum Manifesto, such a thing will come in maybe 10 years. It shows that if you pour a few $100 million into something like Google did, you may be able to achieve some significant progress, which is the reason of developments that we will discuss maybe afterwards in science policy in Europe now. In any case, the point is that, you know, now it has been achieved to show it is possible. Before we didn't know. It was an enormous engineering challenge, more challenging than, as some colleague put it, keeping a snowball solid in the middle of hell. Because this snowball, those qubits, this little snowball of 50 qubits is in an environment which is very hot, because these things need to be at basically 0 temperature or slightly above 0, and keeping them isolated and functioning in a quantum way is extremely challenging. So this is the impact that has been achieved, the quantum brother rights flight. But now, what we expect in the next 5 years, and actually there was a science paper, I think, coming out in the last days from Google about the first applications, for instance, to quantum simulation. What is that? Well, before we have the fully connected, perfectly error-corrected, universal quantum computer, we can already do some very useful things in the field of quantum simulation. What is that? That is, I use my individual bits, like my individual atoms, to simulate, to reproduce the behavior of some other systems in which I have atoms together, like a new material or a new chemical compound. And what is the impact we expect from that? Well, actually, in Europe, here and in this case in Munich, we already have examples of first problems in which a quantum simulator can outperform the fastest supercomputer. Again, for some academic problems which only interest scientists or theorists, again. But the next step, which Google is starting, as well as many others, and we in Europe, we are very strong on this, including this place in Munich, but also in Italy, there are some very important groups, and as well as in other places, trying to use quantum simulators, special purpose quantum computers, to develop those new materials, those new chemical compounds. This can be used for drug development in the future, without the need to test on living beings to some extent. So what is the impact there? It's not like any one of us will carry a quantum simulator in their pocket. Maybe yes, but not that we know now. But what will we use? We will use the new materials, the new chemical compounds that can be developed if we manage in the next 5 to 10 years to make those quantum simulators able to give a real quantum advantage. Now, Google, what they did, they call it quantum supremacy. And in light of some recent developments, they now regret having used that term. And now they regret it even officially. I'm preaching since 5 years that it is not a very, very good idea to choose that. But in any case, now they acknowledge that. But this is just, a historic accident, so to say, because of course they didn't mean anything bad, like many other of their colleagues on the other side of the Atlantic mean when they use the term supremacy. But so what they meant was just some quantum computer which does something which is beyond what the classical computer can do. And they did it. But now the next impact, which is important for society, is quantum advantage. When this is really bringing advantages to the users, to the citizens, in this case, for instance, for new chemical compounds and materials which we can develop and understand with quantum computers. Now there is a third aspect, a third field, which we should mention in terms of impacts and what is already available now, which is sensing. This is also something which Jose Ignacio mentioned, and he did say, and this is particularly true in this field, that it is a continuous progress in that field. So what is quantum sensing? Again, the idea is I'm using individual quantum systems. So now I will take an individual electron. This is the tiniest magnet that exists. So if I put this magnet near a very faint magnetic field, like the one created by a neuron, then the electron goes. Because, even a very tiny field can be sensed by that. So what's the impact of that? Well, this is in the medicine. For instance, for diagnosis, you can detect single neurons in real time. It has been shown in vitro, not yet in vivo. It can be used not only for diagnosis, but also for such things like a project which the company Bosch has, a pilot project in the German program, we will come back to that later, in which they are equipping a helmet with such quantum sensors with the goal to read some elementary brain activity and establish a human-machine brain interface. Like you think something elementary like mouse go to the right, and the mouse on your computer goes to the right, which may not seem a big deal, but if you suffer from, for instance, lock-in syndrome, that might end up being your only way to communicate to the outside world. So just a very basic function like this can have a huge impact in medical therapy. And of course, it's easy to imagine that if you develop that, it can help us understand better the brain and perform a lot of other diagnosis tests. So this is just one example of impact of quantum sensing. Other examples are, for instance, satellite navigation, where you can know where your car is with millimeter precision, and many others, which we may discuss afterwards. But there is really a broad range of such impacts which we are working on and which are in our research agenda for the flagship.
Yes. Jose Ignacio, would you like to add comments?
Yeah. Well, where we are in quantum technologies, in deploying quantum technologies to industry, let me frame this a little bit. So as is often explained from the laboratory to something which is useful, you have to go from the research process. You have to do a lot of research. Then you have to do a lot of development of what is the idea, finally, that you want to implement based on some fundamental facts that you have discovered in research. And then finally, you have to do some innovation. You have to do a real product. So this is a famous R plus D plus I. And the relevant thing is that R and D cost money, whereas you get back your money from the innovation. So in this road that takes from the lab to the final product, I think quantum technologies have shown the research part, that there are principles that work, and we are now doing the development part. So some of the ideas that are being pursued by the community are at the level of the development, and also of the research. But there is very little going on till now at the level of innovation, real innovation. So let me give 3 examples of these. And one of them, for instance, is here in Singapore, is about communication. We do know the principles. We have, as Tommaso mentioned, BB84, we have Eckert 91. We do have the protocols. They have been shown to work in labs and also in some situations, but they do not provide now a solution for a country. They are not at the level of producing the solution for everybody. So what we are doing here is that we are now trying to team with a corporation which is in charge of deploying optical fiber in all Southeast of Asia. What is the idea? That we make the country ready for quantum communication, for secure quantum communication. So there is still the need for this enormous step of development that costs a lot of money before we get to the really innovation, to the fact that all our communications will be done with the quantum protocols. In sensing, what we are doing is that we are now looking for end users, real end users. So in particular, the example I would like to bring here is the one of accelerometers, and in particular, the use of accelerometers for navigation. So we think that navigation is one of the fields where sensing, quantum sensing, will make an impact. So we are trying to develop solutions for this. It's, as you see, as scientists, as basic scientists, it takes an effort to change the language, to change the course, to change our dynamics, while keeping curiosity-driven research. So it's a balance which is not at all trivial, and we need the help from industry. So I do believe in hubs, in ecosystems. I do believe in places where the interests should merge and collaborate. And for computing, let me say that I'm also a believer of the use of very small quantum computers that connect to each other. I think this is the relevant key. I foresee in the next 5 years the emergence of the first small quantum computers yet connected. So they can share entanglement, they can share states, they can manipulate the state and pass it to the other. They can produce blind computation. They can certify that I'm talking to somebody who has quantum capacities, that they can prove that they have a quantum computer. So you can certify in this way. So I see the emergence of the mixing of communication with computation as a relevant field in the short future. But as I said, in my opinion, all of them are at the early stage of development, not yet of innovation.
Okay. So there are, before we move, I mean, there are already questions from, several questions from people connected online, of course. If anybody in the audience would like, please ask. So I just go through them, and they're for both of you. And one question was, I think that is related to cryptography, and they would like to understand what is the influence and impact on intelligence communities, if there is already. And then two more clarifications are asked about what is the exact meaning of quantum repeater, if you can say more about this, and the difference between just photons going through fibers and light. Probably between, I guess it's about quantum and classical propagation. So, yeah.
Okay, so I can take the one on, well, I can take all of them. Jose Ignacio, which ones do you want to take?
So I think
yeah, security. It's okay. Let me, Tommaso. I just say a few things about security, and that's it.
Why not?
Indeed, the relation of crypto to security is absolutely impressive. I mean, in all the cybersecurity conferences, there are sections on quantum cryptography. There is a double fight. One is whether quantum computation can break classical cryptography, and how then to secure yourself. And this can be done either by post-quantum cryptography, that is the discovery of new algorithms that can preserve secrecy while using classical channels, not using quantum, but classical channels. And the second is really to substitute all the classical by quantum, okay, with all the difficulties that this may incorporate, like that you need quantum channels. So this is a relevant thing. I think that all of us in the community have participated in these kind of conferences, and it's simply amazing. The world is now dominated by a level of politics that imply a lot of cyber war around the planet, and there is the need by corporations and states to be protected. So, and they look obviously to the ultimate solution, which is promised by quantum mechanics. So I think this is absolutely essential. And we will see only a growth of the relations between the world of security and the world of quantum mechanics. Go ahead, Thomas.
Well, I have a little story. When the Dalai Lama went to Innsbruck, he actually went to that cellar on the way to going, as I mentioned, to Anton Zeilinger, who had that year realized quantum teleportation. based on entanglement. And entanglement is a correlation between particles which you can use for such secure communications. So, what is the connection to security? Well, Anton said immediately, he saw immediately the possibility to use this, including because, again, Jose Ignacio's predecessor, Arthur Eckert, the theorist we mentioned before, had invented in 1991 a protocol to use entanglement for secure communications. And so Zeilinger went to the European Space Agency and said, look, we should put this on a satellite and use it for secure communications. And the European Space Agency slept on it for the good part of 20 years. And the first author of the paper on teleportation, whose name is Jan Wei Pan, and he, as you can guess, is not exactly Tyrolean, he went back home and he got from President Xi $2 billion to make a quantum satellite for secure communications. And indeed, 2 years ago, they realized a quantum secure video conference via satellite between Beijing and Vienna, between the two presidents of the Academies of Sciences, because of course this was scientific cooperation, but obviously this has very deep implications for the intelligence community, as had been asked. And the point is that, again, is this a technology which is unhackable, which we want only other people to have, whereas they can listen to our communications, or is it something that we want also to be able to use? And by the way, the Americans also have a quantum satellite in orbit, only it is in a dark program, so we are not going to read this on newspapers. However, I'm not going to be killed for having told you, because I heard it from some people who know very well, which were of course not supposed to tell me, but nevertheless it is a sort of a non-fact. When I went to the White House, I was teasing them by telling them, you know, we know that you have a satellite up there, even though it is in a dark program. And the comment was, oh, we are not supposed to talk about that, which is a clear answer about the question, right? So they do have it, the Chinese have it. Do we want to be the only ones who don't have it? This was among the arguments which I discussed with Commissioner Günther Oettinger in a hall of a hotel in Stuttgart 4 years ago, when this whole thing was started. And this is becoming more and more relevant for the intelligence community, as now we are creating this European quantum communication infrastructure, which actually was co-initiated by Italy. And actually, the meetings, for the first time in the history of our community, the meetings of this committee are just being classified, because this is information which can no longer be shared broadly because of the security implications. Now, there was also a question.
Sorry,
yes.
no,
Yes,
sorry, before, because
yes.
One question is tightly connected to what you say. Is this Quest program, this Chinese-Austrian program that you were discussing?
Yes.
Okay.
And this is, as I mentioned, a purely scientific program, in the sense that they developed jointly some science experiment, and this is why the two presidents of the Austrian Academy of Sciences and Chinese Academy of Sciences did that. And actually, I asked, because this is something which is, of course, very sensitive, so I discussed this with Anton Zeilinger last year, and he explained that this is purely scientific, and there is no secret aspect into that. But of course, the know-how which is developed, I mean, there is no way to tell how the Chinese government is using that knowledge, and we do know that, of course, they are using also for these purposes, which is, of course, perfectly legitimate. It's an application of science for something which they regard as an advantage to their society. And the whole point we are making here is that it does make sense also for us in Europe to use in a similar way the know-how that we have for the benefit of our society, including in the security aspect. And this is indeed among the motivations, as I said, why we are investing in that. Now, there was a question, what is the difference?
Quantum repeaters. Sorry.
Yeah,
yes.
that's right. So let's do the photon and light and then the quantum repeater. So, light is a lot of photons, like very many photons. Now, if I turn down the power of the light, then I still have very many photons. And then if I still turn down more, then I still have many photons. And if I go on and turn down and down and down, at some point, the light will stop getting to, I don't know, some screen, you know, as a wave, and it will start getting to the screen as dots. Pick, boop, 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 little points. So the light, when it is weak enough, is no longer consisting of a continuous wave, but is only traveling in small packets. And those small packets of light, which you really can measure, because you can see, you know, there are experiments, you can see videos on the internet of those photons coming one by one, and then after you got many of them, then they start reproducing the behavior of some wave optical pattern. So this is, photons are very, very weak light when you have the smallest possible unit, in the very same way in which atoms is very, very, very rarefied matter, in which, you know, instead of having some very solid thing consisting of many atoms, you take the smallest possible part of it. It's the same thing. Now, what about quantum repeaters? So those photons, the problem of those photons, if I send them one by one, is that, as we said, if someone measures that, then the photon will change their state. In many cases, it will be absorbed. And this includes a possibility in which the photon is traveling, but at some point it gets absorbed just by the optical fiber which it is going through. And the problem is, how do I make sure that my entanglement for my teleportation or my quantum cryptography is distributed between, not only between here, Trieste, and let's say Padua, you know, a couple 100 kilometers away, but between here and maybe Rome or Berlin or elsewhere. If every few hundred kilometers the photon would get destroyed. So I have to, you know, let's say, share a photon, entangled, correlated, one between here and Padua, and one between Padua and Bologna, and one with Bologna and Firenze, and another one with between Firenze and Rome. And what I do is now I want to get my photon, which is here, entangled with the one in Bologna. In the middle is Padua. So in Padua, I need a quantum repeater, a little quantum computer. This makes some quantum operation. It is the C naught, which was mentioned before, but it doesn't matter so much now. The point is some quantum operation of a quantum computer, which essentially is doing some teleportation. So the entanglement, which is in Padua, together with Trieste, gets teleported to Bologna. So in the end, I have entanglement between Trieste and Bologna. And then I want to have entanglement between Trieste and Rome. So I will do my operation in Bologna. In the meantime, I have done it also in Florence, so that I have Bologna, Rome. And then now I do my operation in Bologna, and over larger and larger segments, I then share my entanglement over larger distances. Once I have it, I can use it for teleportation, for quantum cryptography. So that's what a quantum repeater is.
Perfect. Thank you. Okay, so I think we can move to the next topic, which is something you both alluded, and you say already something about it. But I think it would be interesting to talk also about the geography of quantum technology activities. So is this something, I mean, I'm referring to Far East, especially Jose Ignacio, Europe, Tommaso, United States. This is something that is being done at the national level. There are clusters. We already heard both of them talking about Europe. I'm curious to know if there is something else of this kind in the Far East. Please tell us a little bit about, I don't know. Jose Ignacio, you want to start?
Yeah, yeah. I think that the audience is mainly European, so what Tommaso will bring will be more relevant for everybody, but maybe you're curious to know how things are evolving here. So let me make a first very general comment, which is that many countries which are not in Europe or North America or China are starting to understand that quantum technologies will probably not be shared. They will be proprietary. So if anybody builds a fantastic quantum computer that can break cryptography, classical cryptography, or can solve quantum chemistry problems, well, this quantum computer will not be shared. This will be proprietary. This is understood by more and more people around the world. And this is the reason why there are an emerging amount of initiatives to create centers which are trying to be, let me say this word, self-sufficient. They can build up in their country the knowledge which is there. In this sense, Europe is the origin of quantum mechanics. Origin has the most amount of talent, in my opinion, in the world. Of course, North America is very powerful, has an enormous amount of corporations and top universities, and very likely is leading the way in many initiatives. And China is simply catching up at an amazing speed. May I say that I have some interaction with them, and not all of them positive from the point of view of science. Okay, so more is said than is really happening. Okay. But then you have Japan, where they are rethinking now a little bit what they are doing. They think that they are not getting what they thought, or they were not investing enough. Okay, so Japan is in a mixture. Singapore has considered now the next 5 years, and they have decided that quantum technologies is one of the 6 subjects that they want to push, and in particular, the effort will be multiplied by a factor. This is also happening in Israel. This is happening in many other countries. But there is a difference. They don't want to have just curiosity-driven research, but they want to have mission-driven research. So the next money that will come in this country is coming with a structure. So you cannot simply ask for calls, for grants, and do your own research, and this research will be evaluated on just on the basis of excellence. But there will be an element of the relevance of the field because it's mission-driven. Okay? And there will also be the need of collaboration. So the two new ideas are mission-driven and collaboration. And I would also like to mention that I'm involved in this initiative in the Arab Emirates, which is a country which is really, I didn't understand it well, and now I understand it much better, and the difference with all the neighbors. It's very complicated for the Arab world if you are not there. Little by little, I'm understanding it better. And this is, again, a piece of the planet where they think that the future needs fundamental research and needs quantum technologies. And the effort is extremely clear. So they have built an institute to develop the fields that they think they are behind, completely behind, and they are trying to import as much talent as possible. So again, here you see a player which is powerful from the economical point of view with a very clear strategy. Okay. And if you look in detail now, you can see the similarities between many of these countries I've been mentioning in the East, that they see themselves as second players, but they have understood that there is no barrier to become a country with with the quantum technologies incorporated in their productive system. So I think that changes in geopolitics, times in geopolitics are changing little by little in a way which is pretty much unnoticed in Europe, but which is very, very solid. Okay? And so if you ask for me what will be the map of quantum technologies in 10 years, I promise you something. It will be surprising for many people.
Thank you, Tommaso.
So what do we have worldwide? Well, I mean, of course, Jose Ignacio already covered a lot of that. In terms of investment, well, we have Japan, which is underinvesting a few hundred millions, but now they realize that they would like to ramp it up. China is claiming to be investing 10 billion euros. Whenever you ask people on the ground, it's actually more like one order of magnitude less. So maybe 10 billions will come, but it's not something which is being seen at the moment. Europe is investing, at the moment we are about, in the planning 1.2 billions. But there is planning also for this, this is for research, and for the infrastructure is more like, 2 more billions for the quantum communication infrastructure, and also the quantum computing and simulation infrastructure, in which you take quantum processors and combine them with existing supercomputers. Plus, and this is the European Commission, plus the member states. So France is about to announce a program President Macron mentioned that a couple of days ago. And what we expect is something of the order, let's say, 100 million a year for the next several years, but it could be more. Chancellor Merkel announced in the German Federal Parliament a program for 2 billion euros just for Germany. She announced that a couple of weeks ago. The US has in the open 1.2 billion National Quantum Initiative, plus in the dark it's actually much more, but we don't know how much. Russia, President Putin announced like a couple of months ago an investment of $700 million to build a quantum computer, and more also sort of classified for quantum communications. So, and there is also a big initiative in Australia with some centers of excellence, also a few $100 million. Plus, in the US, the major companies are investing massively. So Microsoft, IBM, Google, Intel, and this is in the order of 100 millions per year each, if not more. So this is getting big.
Giuseppe?
Yes, you mentioned already Bosch before, the helmet. So more about connection between industry and academy. So how is industry responding to this?
Yes. So I have a little story for that. Because 4 years ago, I went to Venice Beach. I can recommend going to Venice Beach anyway, It's a nice place around Los Angeles. There is a little bit too much pot for my taste going on around there. But anyway, you go there, nice beach. And the reason I went there on behalf of the European Commission was asking Hartmut Neven, the boss of Google's Quantum Artificial Intelligence Lab, which has their headquarters there, the following question: what can we do to stimulate a comparable level of engagement from industry in Europe as we see in the US? Because in the US it's very strong. And Hartmut Neven's reply was, you cannot, because you do not sit on a pile of cash. So when I came back to Europe, I had a dinner with Volkmar Denner, the CEO of Bosch, and I said, look, this is what Google is telling me. Do you have any counter-argument to bring to the Commission? And he said, no, he is right. And why is that? Not because the European industry is afraid of risk. It's simply because they do not sit on a pile of cash. They do not sit on the huge profit margins which were made from the internet revolution, which was started by some physicists in CERN, the web, and then, none of the money, or essentially none of the money, was made in Europe. So that our companies have a strong interest, but not so much on cash to invest, which is among the reasons why companies supported us very strongly in rallying with the Commission to support this, and this is why the Commission is coming in, both with the supporting research, but also with the first wave of procurement, like to start to bootstrap a market, for instance, in quantum communications, with this infrastructure thing. And actually, for the European quantum computing and simulation infrastructures, I had discussed plans about this with Thierry Breton when he still was only the CEO of Atos 1 year ago, before he was nominated by Macron as French commissioner. And he was a very vocal supporter as an industry leader of quantum technologies. Atos, for instance, the hardware company in France, which he was chairing, developed a first quantum emulator. They call it a quantum learning machine. It is a classical computer which simulates the behavior of a quantum computer. And he is also very strongly supporting this. He also created activities in the space sector, finally, 20 years after Anton Zeilinger failed to convince the European Space Agency. So it is starting, there is strong interest. I am actually, so the thing I'm working on mostly now that the flagship is on its way, and that the funding seems to be rather stable for the next years, what I'm working on mostly right now is the European Quantum Industry Consortium, which I call the QUIC. It has a nice pink logo, like the flagship. And we had a first kickoff meeting with more than 150 companies from all over Europe to start that. So we have a series of activities or working groups. We are creating an industry roadmap for quantum communications. How do we make those thousands of quantum key distribution, quantum communication devices which are needed for the infrastructure? How do we make sure that they can be produced in Europe? Yeah, because we also have issues like ID Quantique, the world market leader, which was mentioned before, is now owned majority by South Korea Telecom. So for this security aspect, which was mentioned, this is not exactly ideal. In fact, we cannot involve them in discussions at this stage. So we really have a huge momentum from industry. This is the main thing which is on my plate at the moment on the organizational side. And this is something which is very important also for the Commission. We are targeting really a big announcement together with the Commission, rallying big CEOs and SMEs alike in the next few months in order really to bootstrap the ecosystem in Europe. But we must admit that due to this missing pile of cash, we lag behind. So there is no question about that. China is huge government spending. US is huge industry spending. Europe is very significant government spending, not yet, and strong industry interest, not yet a real thriving ecosystem making money out of it. This is our challenge for the next 5 years.
Jose Ignacio, what about Singapore, Far East?
Yeah, I agree completely with Tommaso. There is a big difference between each continent. China, not only they have the government funding, but they also have companies like Baidu or Tencent. They have teams for creating a quantum computer. The big difference is, as Tommaso said, that there are corporations in the States that have a lot of money or cash, okay? And it comes from the internet revolution. Whereas in Europe, we have companies that are very solid, okay? Think of the telecom companies, they move a lot of money. But they are not eager to make investments which are not clearly related to an improvement of their results. Instead, there is a lot of money in Europe which is in the hands of investors. So this is for me the challenge. The challenge is that in the planet we have researchers with ideas, we have companies that I see them as end users. And often we need a glue to put that together, which is the money, which are the investors. So this is what I think that, or at least this is what I'm trying to do here in Asia. What I'm trying to do is to put together in the same room the generator of the ideas, which are the scientists, the possible end users, which are companies and corporations, and the money, investors. I think that there is a combination of the three that is absolutely necessary to make the final push to bring quantum technologies to the realm of, to the society. And this is certainly what in Europe should happen. Okay, as far as I can tell, none of the companies I've been meeting have the strength, the muscle of the large American corporation. So Europe needs to include an element which are investors, essentially. And at this point, let me mention that investors could be the very same European Union, mechanisms that should be triggered by the European Union. There is an example here which is amazing, which is that Singapore, from many, many years ago, started to create a separate holding, which is called Temasek. That I don't know the numbers, but I think, I don't know, it's an enormous amount of money, really out of proportion. And they used that in the past to develop the country in a significant way. For instance, airlines were developed with this Temasek funding. So they have developed a mechanism to help the transit from ideas to reality, which has financial muscle. So I think this is the critical step in Europe in particular, to put together the three parties, okay? Not simply research and companies. I think one should include the most powerful funds that there are in the planet. There are many, by the way, in Japan, in Europe. To give you an example, one of the large UK funding investors are setting office in Singapore, and the first thing they did is to talk to us. Okay, so I think there is obvious space to put into the equation the money part.
So yes, I didn't address the investment part because we were speaking about the question of what about industry. But of course, in this quantum industry consortium that I initiated a couple months ago, we do have a working group in which venture capitalists are coming, and there are several prominent venture capitalists from all over Europe which are coming there. And this already had a couple of workshops at the European Investment Bank, because the European Investment Bank also wants exactly to create some effect like that. So we are starting. So this is something which really came up in the last year or so, but there is a lot of interest in this direction, and we hope, I cannot say more about this, but I hope to have some interesting announcement in the next couple of months.
Thanks.
Okay.
May I add,
Sure.
Saro, may I add? No, just as I'm very happy to hear that, Tommaso. I think this is fundamental. And I would add that we have to be very careful of all of us, all of scientists, because, you know, the hype around the quantum world, the quantum word, let me say, just quantum itself, the word is a hype. It has positive effects and negative effects, as we all know. So we have to be very careful that the promises are adequate. They are balanced against the reality. Otherwise, we risk the fact that all these investors may think that it was too premature, and and we are provoking quantum winter, as many people say, and this has to be considered very, very seriously. Okay.
No, but
so I would like.
No, go ahead.
To see very. No, I just. I prefer to have few things, but extremely solid, and with a clear understanding of the timing, which is what many people from the industry don't quite understand, or they think that they can put pressure and change the natural timings of science, which is, I would know is not possible. No? I mean, we need our time. So just a word of caution that, it's worrying me, which is not that positive.
No, this is wonderful. So let me escalate that further, because there was no question about hype, and I'm glad that Jose Ignacio mentioned that. Well, actually, he said he wants few and solid things, and I say I want many and solid things, but solid means the following. So I have a little story for this. Last time I was in Silicon Valley, shortly before the crisis, it was last December, for the annual Q2B Quantum to Business conference. A lot was about the strategic aspect of, sovereign technologies, export control, dual use, and stuff like that. And everybody was speaking about export control. And in my talk, I said we need much less export control. We need much more hype control. Because I heard in that conference from industry, actually, not from the scientists, but from industry, statements like, in 2 years, quantum computers will be able to develop new drugs for humanity. And this is something which needs to be characterized with a very bad swear words, which I will not use here for the purpose of YouTube followers, okay? And after my statement, we need hype control, a lot of people, including those who made these statements in their speeches, came to me and said, oh, you know, you are so right, that's very important. And then I say, but then why on earth are you making those completely false statements? Because they say, oh, but you know, we have to convince our CEO. So there are then two possibilities. Either the CEO is an idiot, and when he will see or she will see in 2 years that this is not happening, they will say, oh yes, for sure, please take another 100 million. Yeah? Or perhaps the CEO is not an idiot, which sometimes happens, and then you have shot in your, you choose your favorite body part in which you want to shoot. So is this what we want? This is really suicide. It's not just we have to be careful. We have to make promises to be very careful in what we state and make promises only about what has a very clear foundation. So the numbers I gave before in terms of years in which we expect things to happen if we overcome the obstacles and so on, those are numbers which come from a discussion among hundreds of experts in the community summarizing our strategic research agenda. And so this is extremely important for advising policymakers to really avoid the hype, to make sure that there are some things which are coming, some things which may come, and some challenges which we do not know whether we will overcome. And this is very important, not only for investors, but coming back to the topic of industry, for industry internally to decide. But it is interesting that, when the pile of cash is available, industry is investing in that. So the US industry is believing very strongly in this. And also the European industry is believing in that. Of course, it will come, step by step, but there are some important promises. We do not yet know all of what the second quantum revolution can and will bring to us, but we know that the promise is high and there are ways to get there. We just have to keep our feet firmly on the ground, as Jose Ignacio thankfully reminded us.
Thanks.
Okay. So I think we are running out of time, so unless there are questions from the audience, I really would like to take the opportunity on behalf of Giuseppe and myself to really thank our speakers, Tommaso Calarco and Jose Ignacio Latorre, for the very interesting discussion we had. I think we can clap, right? Because there are people here.
Can we clap? Oh, wow.
So it's pretty exceptional to clap these days. You just see images moving.
You wave your hand
exactly.
to do something.
Okay, so thanks a lot to everybody and thank you for listening. Bye-bye, Ignacio. Jose Ignacio.
Bye-bye, Jose Ignacio.
Bye.
Bye-bye, Saro, Tommaso, Giuseppe. Bye-bye. Pleasure.
Ciao.
Ciao.